So for this question then, we're given this expression here and asked to approximate it then for small values of theta, where theta is measured in radians. Now you should be familiar with this result, that for small values of theta, when theta is measured in radians, sine theta is approximately the same as theta, and cosine theta is approximately the same as 1 minus theta squared all over 2. So what I'm going to do here is just replace the theta with 4 theta when it comes to using cosine of theta, this approximation here. So we've got on the top here 1 minus, then I'll put in square brackets here, what we've got, which will be 1 minus, and in place of that theta then we write 4 theta, and it's the 4 theta that is squared, and that's all divided by 2. I'll just close off that square bracket there. And then in the denominator here we've got 2 theta, and in place of sine 3 theta I just replace the theta here with 3 theta, so it's going to be 2 theta times 3 theta. So it's just a question of simplifying this. So we've got 1 minus 1, so that goes out, and we've got minus minus there, so that's a plus value. So you've got 4 theta squared, that's 16 theta squared divided by 2, so you're going to get 8 theta squared on the top. In the denominator, 2 theta times 3 theta, 6 theta squared. And you can cancel this down, the 6 and the 8 can be divided by 2, so that's 4 and a 3. The theta squareds cancel themselves out, and you're left then with just simply 4/3. Okay? Now for this question, we're given the curve C has this equation for x greater than 0, and asked to find dy by dx, d2y by dx squared, verify that C is a stationary point at x equals 4, and determine the nature of the stationary point giving a reason. So to do this, we should be familiar with basic differentiation. For dy by dx, for x squared, just multiply by 2 and reduce the power by 1, so you're going to get 2x. For the next one, minus 2x, that's 2x to the power 1, it's just simply 2 times the 1, which is 2, reduce the power by 1, that's x to the power 0, which is 1. And then we've got minus 24x to the power half in place of root x, so it's going to be minus 24 times the power a half, and reduce the power by 1, so it's x to the power minus a half. And if you clean this up, you're going to end up with 2x minus 2 minus 12 x to the power minus a half. You could leave it like that, or you could write x to the power minus a half, remember, as 12 over x to the power half, or even 12 over the square root of x. Now for d2y by dx squared, differential of 2x is simply 2. Differential of a constant, that goes to 0. For minus 12x to the minus a half, you just got to do minus a half times minus 12. That's going to be plus 6. And then reduce the power on x by 1. So that's x to the power minus 1.5, or minus 3 over 2. Okay? Right, so verify that C has a stationary point at x equals 4. Now, because it says verify, we don't have to equate the equation dy by dx equal to 0. All we need to do is substitute x equals 4 into dy by dx here and show that it equals 0, and then state that if it does equal 0, we recognise that it's a stationary point. That's a very important point to do. Okay, so I'm just going to say that when x equals 4, substitute it into dy by dx, so we get dy by dx equals, and we've got 2 times the 4 minus 2 minus 12 times x to the power minus half. Remember, that's 12 over x to the power half. X to the power half means the square root then of whatever x is, so it's going to be the square root of 4. Work that out and you've got 8 minus 2, square root of 4 is 2, 12 divided by 2 is 6. Okay, so if you work that part out, you can see you get 0. But as I said, don't leave it like that, okay? Show the examiners that you know that that means that you've got a stationary point, okay? Now for part C, we've got to determine the nature of the stationary point, giving a reason. Well, this is easy because we've already been asked to find d2y by dx squared. We've just got to substitute x equals 4 into there and check out what sign we get. By substituting x equals 4 into here, we find that d2y by dx squared equals 2 plus 6 over x to the power 3 upon 2. That is the square root of whatever x is, which is 4, and then we cube it. Well, the square root of 4 is 2, so 2 cubed is 8, so you end up with 2 plus 6/8. That's going to give you 2 3/4, or 2.75. I'll just leave it as 2 3/4. More importantly though, this is a positive value. And when you get a positive value for d2y by dx squared, it represents a minimum point. So therefore, what we have is a minimum. Okay? Don't just leave it at greater than 0. Give a reason why that stationary point is a minimum, because it's greater than 0. Okay? Okay, so for this question then, what I've done is sketched out the sector we're given, where the angle here, theta, is measured in radians and the radius is r. We're told that the area of the sector is 11 centimetres squares, and also given this fact that the perimeter of the sector equals 4 times the length of the arc AB. So we've got to find the exact value of r. So what I'm going to be doing then is just form an equation from this first statement up here about the area, and then we'll form another equation from this statement here, and we should be able to use simultaneous equations to eliminate theta between them and figure out what r is. Okay, so let's start then with this first statement here, that the area of the sector is 11 centimetres squares. So you should be familiar with the fact that an area of a sector is a fraction of the area of a circle. That fraction is theta, if we're measuring it in radians, theta compared with 2 pi. And it's that fraction of the area of a circle, so that's going to be pi r squared, and it equals 11. Most probably you might not remember it as this formula. Those pi's cancel, and you might just remember it as the formula a half theta r squared, which equals 11. Either way, it doesn't matter, you're going to get down to this equation, and we want to make theta the subject. So if I just multiply through by 2, that would be 22 there, and divide both sides by r squared, we get theta equals 22 over r squared. Okay, so that's our first equation for theta in terms of r. Now what I'm going to do now is just call this equation up here 1, and we're going to build from that. So we'll start up here and just say from 1. Okay, from 1, let's build up that equation. Now when it comes to the perimeter of the sector, the distance all the way round, then what we've got is r here and another r there, so that's going to be a total of 2r. And then to that we've got to add this arc length AB. So the length of an arc is again a fraction of the circumference. So that fraction will be theta over 2 pi radians, and the circumference of a circle will be 2 pi r. So it's theta over 2 pi times 2 pi r. And that's going to equal 4 times then the length of the arc AB. So we'll have 4 there, and the length of the arc AB again is going to be theta over 2 pi times the 2 pi r, the circumference. Now you might not know the formula as this for the length of an arc, because those 2 pi's cancel one another out, just leaving you with theta r. But that's how it's derived anyway, okay? Those 2 pi's there cancel out. So we just need to tidy this up. And we've therefore got 2r here, and we've got a theta r here and 4 theta r. So if we just take theta r from both sides, that's going to leave us with 3 theta r. And you'll notice now that the r's cancel here on both sides, so I might as well take them out. Now all I need to do now is just sub the value of theta that we found down here. So I'm just going to say sub for theta. Okay, and if we do that, then we've got the 2 equals 3 times theta, that's 3 times the 22 then over r squared. And what we get now is that 2 equals 66 over r squared. Just times both sides by r squared and divide by 2, and you end up with r squared equals 33. And from this, it follows that r equals the square root of 33. We want the exact value, so just leave it as the root of 33. It's not going to be plus or minus because the radius obviously is a positive value. And I'm going to put the units in. R is measured in centimetres. Okay, so hope you're able to see your way through that if it caused any problems. So for this question then, we're given the curve with equation y equals 2 times the natural log of all of 8 minus x. And it meets the straight line y equals x at the single point x equals alpha. And we're asked to show that alpha lies between 3 and 4. Now in order to do this, the method I'm going to be using is a change in sign method. What I need to do is state that at the point of intersection we know that the y values are going to be equal. So at that point of intersection, x will equal 2 times the natural log of all of 8 minus x. And then I'm going to subtract x from both sides, so I get an equation that equals 0. And I'm going to let the left-hand side of this equation be f of x. So we've got f of x equaling that left-hand side. Now if I was to draw this graph, not that I know what the curve looks like, I'm just going to set up some axes here, okay? I'm not saying this graph is going to be accurate in any way. Let's imagine then that this is the point 3 here, and we've got the point 4 here, all right? Not drawn to scale. Then what I'm going to be doing is checking the value of f of 3, see whether it's positive or negative, and the value of f of 4, again checking to see whether it's positive or negative. And what I'm hoping for is that across this interval there'll be a change in sign. That is, the graph either goes from a positive value to a negative value, or from a negative value to a positive value. And that will indicate to me that, assuming then that the curve is continuous, there's no breaks in it, that there will be a root, which is alpha, in this interval. All right? So we now have to go on and find out f of 3 and f of 4. So if you put 3 as our x value into here, you're going to have 2 times the natural log of 5 minus 3. Work that out on your calculator and you'll find it comes out to a positive value, 0.2188 and so on. And when I work out f of 4, then we do indeed get a negative value now, minus 1.2274. and so on. So what I've got here then is a curve that at 3 it's a positive value. Okay, let's just say it's there. At 4 it turns out to be a negative value. Let's say it's there. So our curve, I don't know what it looks like, but maybe it's that kind of curve. Who knows? But what I do know is that knowing that it's continuous, that there must be a root then where it crosses the x-axis, where it equals 0 here. That root is alpha, and it lies between 3 and 4. Now you don't need to draw this graph on here, but you do need to be able to show that there is a change in sign, and you need to write a conclusion, something along these kind of lines, that there is a root alpha in the interval 3, 4, since there is a change in sign, and the curve is continuous over that interval. It's important then that you get the fact that there is a change in sign, and also there's no break in the curve, that it's continuous across that interval. So do state those facts. Okay, so hope that's been able to help you if it caused any problems. Okay, so for this question, we're told that the student then uses this iterative formula to work out an approximation for the root where the graph y equals x crosses this graph y equals 2 times the natural log of all of 8 minus x. That root being alpha. And we've got to say whether using this first approximation of x1 equaling 4 will give us an approximation then to alpha. And so to answer this, what you'd need to do is draw a cobweb graph on top of this graph here and hope that it spirals in. We take our first approximation, x1 being equal to 4, and from here we draw a line up onto the graph of y equals 2 times the natural log of 8 minus x. When we substitute 4 into here, it gives us the corresponding y value. Okay, that will be this one across here, right? But you'll notice I've stopped it at this point here because that y value is the same as x. If I was to come down here, that value of x, let's just do it in green, okay, would be a value down here. And this becomes our new x value that we're going to substitute into this formula here. It would be x2. And with that value of x2, we would substitute it back into our equation and it will give us a corresponding y value. If I come up here, we substitute it into the equation and you can see it would give us this y value here. I would take that y value, okay, and it would be exactly the same as this x value if I projected downwards. Okay, let's project downwards, it would come down here and this value here would be our new x value and it would be called x3. And if I take that value of x3, substitute it into here, it's going to give us this value here as our y value. And can you see it's starting to spiral in towards our root alpha? If I was to do this again, this would be our new x value. I'd project it down to here and let's say we call it x4. Obviously it's getting a bit cramped here, so I wouldn't be able to keep drawing this in, but hopefully I've done sufficient here to be able to demonstrate that this is spiraling to the root. But if I was to carry on, that value of x4 would be substitute in, give me this y value here, and I come across here, and as you can see, hopefully I'm getting closer to that root alpha. So there's my cobweb design, and the conclusion then is that this formula can be used as an approximation to alpha since the cobweb graph spirals inwards towards alpha. So that's basically it. I'm sure you don't need to write in these values for x1, x2, x3, x4 and so on, but you do need to show at least 2 spirals inwards, okay, and write a conclusion stating then that that graph spirals inwards towards alpha to justify the use of this iteration formula. Okay? Okay, just in case you're not looking at this question on my website, briefly we're given that y equals 3 sine theta all over 2 sine theta plus 2 cosine theta, and asked to show that dy by d theta is given by this constant a, which is a rational number, all over 1 plus sine 2 theta. So how do we do this? Well, we've got to use the quotient rule. Should be familiar with this if you've been watching tutorials on my website. Briefly though, if y equals u over v, where u and v are functions of theta, dy by d theta is given by this equation here. And it's a good idea to write down what u is. It's going to be the numerator here, 3 sine theta, and v is 2 sine theta plus 2 cos theta. All right. Okay, so we're ready to use this formula then to start to differentiate y with respect to theta. So if we do that, then we've got that therefore dy by d theta is equal to, and I'll just draw a long division line here. Okay, so we've got basically the bottom of the fraction multiplied by the differential of the top, first of all. So if we take the bottom of the fraction, it is 2 sine theta plus 2 cosine theta, and then we multiply this by the differential of the top of the fraction. Differential of sine theta is cosine theta, so we end up with 3 cosine theta there. All right, so that's the first term here. Now we've got to minus the top of the fraction times the differential of the bottom of the fraction. So we've got the top of the fraction, 3 sine theta, and that's being multiplied by the differential of the bottom of the fraction. So the differential of 2 sine theta is 2 cosine theta. Remember now that the differential of cosine theta is minus sine theta, so this becomes minus 2 sine theta. All right, so that's the top part. Now it's all divided by the bottom of the fraction squared. So we've got all of 2 sine theta plus 2 cosine theta, and all of that is squared. All right. So it's just now a question of tidying this up. So if we expand the first bracket, multiply this bracket with 3 cosine theta, we're going to get 6 sine theta cosine theta. All right. And next we're going to get 6 cosine squared theta, 6 cos squared theta. And then we've got minus 6 sine theta cosine theta there. All right. And finally, we've got plus 6 sine squared theta. So plus 6 sine squared theta. All right. And all of that is over our denominator squared. So squaring out a bracket, then we square the first term here. That's going to be 4 sine squared theta. And then we get twice the product of these two terms. So the product gives us 4 sine theta cos theta. So if we double that, we're going to get plus 8 sine theta cosine theta. All right. And now we square the last term there, so if we square 2 cosine theta, that becomes 4 cos squared theta. Now if I tidy this up further, let's just put a long line here. I can see that this term, 6 sine theta cosine theta, cancels out with minus 6 sine theta cosine theta. And that just leaves me with 6 cosine squared theta plus 6 sine squared theta there. And I can pull out a 6 between both those terms. So we get cosine squared theta plus the sine squared theta. And in the denominator, I can see here with the 4 sine squared theta plus the 4 cosine squared theta, if I pull out 4 there in front of those two terms, I've got sine squared theta plus cosine squared theta. And then lastly, for this last term here, I get a clue here because when I look at the denominator here, I can see sine 2 theta. And you should be aware that sine 2 theta is 2 sine theta cosine theta, and that's looking very much like this. So I could just write this as plus 4, and then in brackets, and I'm going to just do this in another colour, as 2 sine theta cosine theta. Alright, so we should be able to pick up now very easily, because hopefully you're familiar with cosine squared theta plus sine squared theta, or sine squared theta plus cosine squared theta. That's a Pythagorean identity, which is 1. So what we have here then is just simply 6 times the 1 there, so that's going to be 6. And in the denominator here, we've got 4 as a common factor, so I could pull that out. And we've got sine squared theta plus cosine squared theta again, which just said is 1. So we've got 1 there. And we have got the 2 sine theta cosine theta. And I'm just going to write that in as being sine 2 theta. So we've got sine 2 theta there. And remember, it will be a plus there. And I'll just close that bracket off. Now the 4 and the 6, they cancel. 2 will go into the 4 and 2 will go into the 6. 3 times and 2 times there. Okay? And we shouldn't leave it like this, although to me it would look nicer written like that. It's quite unusual to write or to divide the 2 into the 3. That will give us 1.5. But I'm going to write it obviously as 3 over 2 because we're asked to leave it as a rational number. Okay, and that will be over 1 plus the sine 2 theta, and that's what we had to show. All right, so quite long-winded, but hopefully not too difficult. But if it did cause a problem, hopefully you've been able to see your way through that one. So thanks for watching, and as usual, if you'd like to subscribe to my channel, that'd be really great. Okay, you'll be kept informed of any updates, etc. All right, so thank you if you do. So for this question, I've just copied down what we were given, and we've got to show that the equation of the line through PA is 2y plus x equals 17. So to do this, all I'm going to be doing is knowing that the form of a straight line just requires the gradient and a point on the line. If I'm going to use, say, y minus y1 equals m bracket x minus x1, should be familiar with that form of the straight line. I've got to get the gradient though, and the gradient is going to be a perpendicular gradient to this line L. And I can get that gradient just by reciprocating and taking the negative of that reciprocal for the gradient of this line. So that's my method. Let's just get into the problem. Let's just start with the gradient of L. You should be able to see that the gradient of the line L is the m value in front of the x, and that is the 2. Okay, So that leads on to the perpendicular gradient, okay, which will be the gradient of PA, okay, and that's going to be the negative reciprocal of this. The reciprocal of 2 is 1 over 2, and then just put the negative sign in front. So a gradient then of that line minus a half. So I'm now in a position, let's just divide this off, I'm in a position to say what that equation of the line PA is. So I'm going to just put a little subtitle in here. Equation of PA is, and I'm going to be using y minus y1 equals m bracket x minus x1. Y minus y1, y1 is a point on the line. The y coordinate we'll be using is the 5 there from the centre of the circle, equals m, the gradient, which is minus a half, times x minus x1, and that is the x coordinate of the centre of the circle, 7. And what I'm going to do now is just times through by the 2, and that's therefore going to give me 2y minus 10 equals, and this is just going to leave me with minus 1 times the bracket, which will be minus x plus 7. And then I can see this is shaping up for this if I just add x to both sides here, okay, and add 10 to both sides. That's going to lead me in to what we have to show. 2y plus x equals the 10 plus the 7, which is the 17. So for this part of the question then, we're now asked to find an equation for the circle C. In order to do this, you should be familiar with the equation of a circle. Let's just remind you, it is essentially this, that if you've got a circle with centre coordinates x1, y1 and a radius r, it has this form here. So we have the coordinates of the centre, we have our x1 and our y1, 7 and 5 respectively. What we don't have though is the radius r. But if we return to the first part of the question, remember we had to find the equation of the line PA. And so what I'm going to be doing is getting the coordinates of P by looking at simultaneous equations. We can equate the equation of the line passing through PA with that of L, establish the coordinates of P, and then from that we should be able to work out the radius PA, and we can substitute our x1, y1 values and r into this equation, and that will get the equation of the circle. Okay, so that's the method I'm going to be using. So if we look then at what we already know, that is the equation of PA from the first part was 2y plus x equals 17. Then for this coordinate point P here, we just have our two equations, y equals 2x plus 1, which I'll call 1, and 2y plus x equals 17. I'll call that equation 2. Solving these simultaneously, all I need to do is substitute equation 1 into equation 2, so into 2. And if we do that, you're going to get 2 times the y, 2 times the 2x plus 1, and that's going to be plus another x, and that's going to equal 17. So just border this off, come down here, and what have we got next? Well, if we expand the bracket out, I can see we've got 4x here plus another x, that's going to give me 5x. And then we've got 2 times the 1, which is 2. Take it away from both sides. 17 take away 2. That leaves me with 15. And if I divide through by 5 to both sides, I therefore have x equals 3. Now I know that x is 3. I can substitute x equals 3 back into equation 1, say. And that will give me my y value. And that leads on to y equaling 2 times 3, which is 6, plus another 1, that's going to be 7. So therefore, my coordinates for P are 3, 7. Now that I've got the coordinates of P, 3, 7, I'll just mark them on here. We're in a position now to get that radius from P to A. We can just use Pythagoras' theorem. Think of this triangle through here, a right angle triangle. Should be familiar with working out the distance between 2 points. It's just essentially the difference in the x coordinates squared plus the difference in the y coordinates squared, square rooted. That will give us that hypotenuse there. So therefore we can work out what the radius is going to be. The radius will be the difference then in the x coordinates, so that would be 3 minus the 7. Okay, or you could do 7 minus 3, it doesn't make any difference. We square that, and to that we add the difference in the y coordinates, so that would be 7 minus the 5 there. 7 minus the 5, and we square that. And normally we'd take the square root of all of this lot, but knowing that it's going to be the radius squared that we want, I'm just going to put radius squared there and do away with the square root sign. And working this out, we've got the 3 minus 7, which is going to be negative 4. Square that, you're going to get 16. 7 minus 5, that's 2. Square that, you get 4. Add that together and you end up with 20. And so now we've got everything we need to work out the equation of that circle C. So just put in a note here, equation of C is, and using our form up here, it's going to be x minus x1, the centre of the circle, which is the 7, that's squared, plus y minus the y1, that's going to be the 5 there, the y coordinate centre of the circle, square that, equals the radius squared, which we've seen is 20. And there's our equation. Okay, so I hope you've been able to see your way through that if it caused any problems. So thanks for watching, and see you in the next part maybe. Now for this next part, we're told that y equals 2x plus k is a tangent also to the circle C, where k doesn't equal 1. And we've got to find that value of k. Well, clearly it's not this tangent, because that will be when k equals 1. But because it has the same form as this line here, it's got the same gradient. It must be a parallel line to the line L. So if I was to sketch that on, it's got to be this line here. And if I call this point here, where it touches the circle, let's say P dash, then all I need to do is establish the coordinates of P dash. So then I could just substitute my value for my x coordinate and y coordinate into here, and I should be able to work out what k is. But it does rely on us getting the coordinates of P dash. But that's very easy, because the displacement from P to A has to be exactly the same as the displacement from A to P dash, because it's the radius of the circle, and P dash lies along that diameter from P through A to P dash. Okay, so what is that displacement from P to A? Well, we can put that in, we'll move over here, okay? We can put that in as P to A, okay? We'll have it as a vector. Going from P to A, we move from 3 units here to 7 units there. That's a distance, or a distance of 4 units across. So that's going to be a vector there of 4 units. And then we move from 7 down to the 5 here. 7 down to the 5 is a displacement of -2 units. Okay. So knowing that, I've just got to go from A to get to P dash, 4 units across, 2 units down. So therefore I can see that the coordinates of P dash are going to be for the x coordinate, we're going 7 plus another 4 units, that's 11 across. And then for the y coordinate P dash, we're going from 5 2 units down, so it's going to be to 3. Okay, so P dash has coordinates then of 11, 3. And all I need to do now is just substitute this set of coordinates into this equation here. Must satisfy that equation because this point lies on it. So I'm just going to say sub in 1, okay, those coordinates there, and we therefore have y, which is 3, equals 2x, so that's 2 times the 11 there, that's 22, plus the constant k. Okay, k therefore must be equal to 3 minus 22, that's going to be minus 19. And there you have it. Okay, our value for k. Hi. Now, what I've got here is an alternative way of finding out this value of k when we've got this equation of a tangent, y equals 2x plus k, we're told being a tangent to the circle C. This is not a method that I would want to use in a question like this, as it's quite lengthy, but nonetheless it's a useful exercise. What I'm going to be doing is substituting 2x plus k for y into the equation of a circle to find out what the corresponding x value will be. What I'm going to be using though is the fact that it's going to turn out to be a quadratic equation, and we know that if it's to be a tangent, there's just going to be one root, one solution. So for that condition to hold, the discriminant of the quadratic, b squared minus 4ac, should equal 0. And that's going to allow me to form an equation in k, as you'll see. And I'll solve that, and I should get my value of k. Okay, so we start then with, for that point of contact, I'm just substituting 2x plus k in for that y here. All right? And what I'm going to do next is expand all of this. And to save time, it's quite lengthy, you'll need to check it out. You should get this result here. When I've squared out this bracket, I've jumped a few stages. We've got 2 terms inside the bracket when it's squared, so remember, you square the first term. So if you were to square 2x plus k, you'll get your 4x squared plus 4xk plus k squared. Then you get twice the product of these 2 terms. So what I've got here is 2 times the product of minus 5 times the 2x plus k, giving me minus 10x minus 5k. And then you square the last term here, that's the plus 25. Okay, so do check that out. Then I've just grouped together all the terms, and if you group together the x squared terms, the x terms, and then the constants, you should find you get this line here. Okay, now we do the bit where we've got a quadratic equation. We know there should be one root, so you would expect the discriminant b squared minus 4ac to equal 0. And the b is this part here, 4k minus 34. We've got 4 times a is the 5, and c is this bracket here. Now if you put that down, put it equal to 0, you're going to get this equation. All I'm going to do now is just expand this, and if you do that, you end up with this line here. You'll see you've got a quadratic equation in k squared. So I just need to simplify this. So if I do simplify that, you're going to get this. And now I can see that I could divide through by negative 4 to each term, and I get a much simpler quadratic equation. And I can factorize this. Factorizing it in the usual way, gives me k minus 1 times k plus 19 equals 0. Now, that would lead to k minus 1 equaling 0, or k plus 19 equals 0. Well, if k minus 1 equals 0, that would lead to k equaling 1. And we know that can't be the case because k cannot equal 1. That would give us this tangent. So therefore, k plus 19 must equal 0, leading to k equaling minus 19. So I hope you've been able to see that method. As I say, it's not one that I would want to use just purely because the algebra is quite lengthy through these stages here. So for this question, we've got to show that this integral, 2 over 3x minus k, integrated with respect to x between k and 3k, where k is a constant, is independent of k. Well, you should see that by differentiating the denominator here, you basically get the constant 3, and we've got a constant 2 on the top, so this is a natural log type. It's based on this idea here, just as a reminder, where if you've got the denominator of an integral is f of x, say, and you have got the first differential of f of x, f dash of x, in the numerator, then it's going to be the natural log of the denominator here, f of x, okay, plus a constant of integration. So I can see that if I pull that 2 out the front, being a constant of the integral, 2 there, we would have 1 then all over 3x minus k. And that's integrated then with respect to x, going between the limits k and 3k. But differentiating the bottom here gives 3, not 1. So what I can do is I can put a 3 there, being a constant, and pull a 3 out the front here as a third. So we end up with 2/3 times that 3 there, gives us 2 all over the 3x minus k, what we had here. But I can now see that differentiating the bottom gives me a 3. We've got it in the top here, and so this leads on to a natural log type. It becomes 2/3 then of the natural log of the mod of 3x minus k. All right? And we've got this in limits, okay, now, so I'll just put some brackets in here, and we've got our limits then from k to 3k. Obviously we don't need a constant now because it's a definite integral, it has these limits. So we just need to substitute our value for 3k in first of all, so we've got the natural log then of all of 3 times 3k, 9k, minus another k, so that's the natural log of 8k. And we've got, substitute the k in, we've got 3k minus k, that's 2k, and we would subtract that value, natural log of 2k. All right, and knowing that k, by the way, is a positive constant, these values are going to be positive, so I don't need to put modulus signs here. So we've got now 2/3, and when we subtract logs, it's the same as doing the division of 8k all over 2k. Should be familiar with that rule. And I can see the k's cancel, left with 8 divided by 2, which is 4. So we end up with 2/3 the natural log of 4. And you can see that, I'll put here, i.e. you can see it's independent then of k. So just write that statement in then, independent of that constant k. Alright, so hope you're able to see your way through that one if it caused any problem. So for this question, we're asked to integrate 2 all over 2x minus k all squared. We're integrating it with respect to x with limits that go from x equals k to x equals 2k. So how do we do something like this? Well, we should be familiar with this particular form of integral. That is, if you've got something of the form ax plus b, where a and b are constants, raised to the power n not equal to -1, then this is a standard result. What we get is ax plus b to the power n plus 1, we add 1 to the power, and we divide by that new power, n plus 1. But we have to multiply this by 1 divided by the a here. What we're doing really is the inverse of the chain rule. So if you're unsure of this, just check out my other videos on integrals that have this form. And we can now turn this integral into this form, because if we just pull out the constant 2 in the numerator, we've got the integral then of 2x minus k all to the power minus 2, because we can bring that up to the top. We're integrating that then with respect to x, with the limits going from k to 2k. So when we compare this result to what we've got here, you can see that if we just take that 2 out, okay, then we add 1 to the power, -2, so we've got 2x minus k, adding 1 to that power minus 2 gives us -1, divide by the new power -1, and we'll divide also by the coefficient of x here, the 2. So I'm going to slip that 2 down there. And I'm going to insert square brackets just between our constant here and the function of x in here. Okay, and so we've got our limits going from k to 2k. So cleaning this up, those 2's cancel, giving us just 1, and I can bring out the -1 to the front, so we end up with negative there, and then I can rewrite this as 1 over 2x minus k. So we'll just put our limits in again in between these square brackets, so we've got 1 all over 2x minus k. Just finish that off there, and our limits k to 2k. So it's just a question now of substituting the 2k in and subtracting what we get when we put the k in. So I'll have the negative here outside, and then what we're going to have is 1 over, and we're going to put that 2k in, so we get 2 lots of 2k, that's 4k, minus the k, that gives us 1 then over 3k. And we subtract what we get when we put k in, so that's 1 over 2k minus k, so that's 1 over k. What we've got here really is a third minus a whole one of 1 over k, and that's just going to give me minus 2/3. So you've got negative of -2 over 3k. Okay, and obviously this gives us a positive value, 2 over 3k. Or you could see this as 2/3 times 1 over k. Either way, what we've got then is that this result is inversely proportional to 1 over k. And that's what we had to show, that the result was inversely proportional to k. Alright, so hope you're able to see my method through there. Now for this question then, we're given the depth of the water d in metres in the harbour at time t hours after midnight. And we've got to find the depth then at 6:30 a.m. And this is fairly straightforward, because all you've got to do is substitute t equals 6.5 into our formula here. Okay, so if you do that, let's say when t equals 6.5, substitute it in, you're going to get d equals 5 plus 2 sine of 30 times 6.5. That comes out to the sine of 195 degrees here. Make sure your calculator's in degrees mode. Work this out and you'll find that you get 4.482 and so on. Round it up to 3 significant figures or 2 decimal places and you're going to get 4.48. Don't forget the units though, the depth is given in meters. And there you go. So for this part of the question then, we're told that what's the earliest time that the boat can leave the harbour, and it can only leave the harbour when the depth is 3.8 metres. We also know that it came in to load at 6:30 AM, took 2 hours to load, so that time t has got to be greater than 6.5 plus 2, or greater than or equal to 6.5 plus 2. In other words, 8.5. So it's just a question then of substituting 3.8 in for d and solving for a value of t which is greater than 8.5. So if you make that substitution then you're going to get this statement here, and just now take away 5 from both sides. That's going to leave 2 sine of 30t equals minus 1.2. Then divide both sides by 2. That's going to give you the sine of 30t equals minus 0.6. And then we need to take the inverse sine to both sides, giving us 30t equals the inverse sine of minus 0.6. And at this point, I'm going to draw a quadrant diagram. So assuming you're familiar with quadrant diagrams, this will be 0 degrees. Turning in an anti-clockwise direction, we'd have 90, 180, 270 and back to 360 degrees again. Okay, so that's turning in the positive sense. Now, we know that sine is negative here, so therefore we would expect the calculator to give us answers in the 4th quadrant and the 3rd quadrant. So I draw 2 lines there, equally inclined to that horizontal. These 2 angles would be exactly the same. When you take the inverse sine of negative 0.6, the answers you get then for 30t turn out to be minus 36.86 degrees, and so on. Okay, make sure your calculator, by the way, is in degrees mode. On the diagram, that's represented as a negative turn, so this angle round here is of magnitude 36.86 and so on degrees. Now, we want positive values for t, so one possible one would be going from here, 0, turning round here to this first line. So that's a possible 30t. And the other one would be starting from here, turning all the way round till we hit that blue line again, this one here, and that is another 30t. So what is the red one going to be? Well, that's going to be 180 plus a further 36.86 degrees. If you do that calculation, you should find you get 216.86 and so on degrees. Underline that as being the red one. For the green one, that's going to be 360 degrees minus the 36.86 degrees. Do that on your calculator, you should find you get 323.130 and so on. Okay, that's the green one, so I'll just underline that as that one. Now we need to divide through each of these values by 30. It's silly dividing the negative one by 30 purely because time's got to be greater than 0. So let's have a look, see what we're going to get for t. If we divide, we'll forget about that one, that's going to be no solution really. If we divide this one though by 30, you should find you get 7.228 and so on. Okay, clearly that's not greater than or equal to 8.5, so that's not going to be a solution. This one, however, when you divide it by 30, gives you 10.5 0.771 and so on, okay? And that's going to be the one that we want. And so we need to convert it into hours and minutes. So it's going to be clearly 10 hours, 10 a.m. okay, and then for the 0.771 you just need to do, in fact, let's just put plus 0.771 multiplied by 60 there, okay, to convert it into minutes. If you do that, you should find you get to the nearest minute 10:46, okay, 10 hours 46 minutes to the nearest minutes. Well, that's going to be 10:46 a.m. okay, to the nearest minute. And hopefully you've been able to see then how I've approached that. Okay. So for this part of the question, we're given the equation of this curve, x squared minus 2xy plus 3y squared equals 50, and we've got to show that the gradient function dy by dx is equal to y minus x then all over 3y minus x. So to do this, you've got to be familiar with implicit differentiation. So I'm assuming that you are. If not, do check out my tutorials on this. So when we get something like this and we're going to differentiate implicitly, I would always encourage you to write an introduction, that is, differentiate with respect to x, okay? So if we start then differentiating the first term, x squared, with respect to x, then that's going to be 2x, so we have 2x there. Now when it comes to differentiating this term, 2xy, we've got to be very careful because we've got the product then of two parts, the 2x and the y, okay? I'll just do a squiggly line underneath there. So I'm assuming you're familiar also with the product rule, where we take one part and we multiply it by the differential of the other part, and then we do plus and we do the reverse, okay? We take the second part, times it by the differential of the first part. So I'm going to take the 2x first of all, we'll put the 2x there, and now we multiply it with the differential of y with respect to x. Well, that's just going to be simply dy by dx. Now, according to the product rule, I plus, and I take my second part here, y, and I multiply it by a differential of this part, the 2x with respect to x, and that's just going to be simply 2. Okay, so we'll just complete that bit there. So that's the product rule then for this term. Now we come on to differentiating the 3y squared with respect to x. We use implicit differentiation here, and that is to differentiate it with respect to y, which will be 6y, and then we put on the end dy by dx. Okay, so as I say, I'm assuming you're familiar with this idea of implicit differentiation. Then we've got the differential of 50, that constant there with respect to x, and that's going to be simply 0. Now I'm going to just expand this out. Okay, we've got the 2x, we've got minus 2x dy dx here, and we've got minus the 2y, and finally we've got that plus 6y dy by dx. And now we need to look at cleaning this up. Well, I can see that we could divide throughout each term by 2. That will make things a lot simpler. So we'll divide through by 2 there, and 2 into that 6 goes 3. So I just need to group up my dy by dx terms here, and by factorising this I can see that we've got 3y here minus x all multiplied with the dy by dx. When you're doing implicit differentiation and grouping up terms like this, always write the dy dx not at the front of the bracket but at the end. So we have 3y minus x, and then we have the dy by dx there. And then I'm going to add y and minus x from both sides, and that's just going to leave me with y minus x. So I'm there now. If I just divide both sides by the 3y minus x, you can see I get the result that we had to show. Y minus x then all over 3y minus x. Okay? Now for this next part, we're told then that for this curve, x squared minus 2xy plus 3y squared equals 50, that the points P and Q are furthest west and furthest east, respectively. And we've already established the gradient in the previous part of the question for any point on this curve. And we've got to find the coordinates then of this point P. Well, the gradient at this point P here, you can see the tangent is vertical. That gradient is going to be infinite. And for that gradient to be infinite, we would expect the denominator here to be 0, because when you divide something by 0, it gives you an infinite or undefined value. So that's what we're going to be working with. We're going to make 3y minus x equals 0. Find out from that equation what x is in terms of y, substitute it into this equation, get a quadratic in y and solve it, and then we can substitute that y value, the appropriate y value, back into our original equation, 3y minus x equals 0, and establish what the corresponding x coordinate would be. Okay, so that's the method, and we'll just crack on then with that. So I'm just going to write a few notes here though, that at P, all right, the gradient we know is going to be infinite. Okay, gradient is infinite, and that means that the denominator in our fraction here, the 3y minus x, must equal 0. And from this we can rearrange it. I should put equal 0 there. We can rearrange it and we can see that x will equal 3y. So if I call this equation number 1 and this equation here number 2, what I'm going to do is substitute equation 2 in 1. Okay? And by doing that, I'm now going to have x squared, which will now be 3y all squared, minus the 2 times the x, which is 3y, times another y, plus 3y squared, and that's going to equal the 50. And we'll just border this off, come down here, and if we carry on, what we've got here is 9y squared. So we've got 9y squared, and then we've got minus 6y squared there, and plus another 3y squared, and that equals 50. So we end up with a total of 6y squared here equals the 50. So we have 6y squared equals the 50. Divide both sides by 6, you end up with y squared equals 50 over 6. That reduces, we can divide top and bottom by 2, and that gives us 25 over 3. So if we take the square root to both sides, y would normally be plus or minus the square root of 25 over 3. Well, we only want the negative value, not the positive value, because the y coordinate P is clearly negative. And if you square root this fraction, square root of 25 is 5, and in the denominator would just leave it as root 3. You could leave it like that, or you might want to rationalize this by multiplying top and bottom here by root 3. And if you do that, you're going to end up with minus 5 root 3 all over 3. Remember, we're forgetting the positive value because since y must be a negative value, must be less than 0. Okay, having got that, we can now substitute that value back into equation 2. So I'll put sub into here. That will give us our x coordinate now. So we therefore have x equals 3 times the y value, 3 times the negative 5 root 3 over 3. And that gives us, well, those 3's cancel out, just minus 5 root 3. So therefore the coordinates of P, if we just summarize, okay, are going to be minus 5 root 3 for the x coordinate, and for the y coordinate it's up here, minus 5 root 3 over 3. Okay, notice by the way how we have to have them in exact form, so just leave them with those root 3's in and express them as fractions as well. So for this last part of the question, we're being asked to show how we would go about finding the most northerly point on this curve, the coordinates of it. Well, what we can see is that most northerly point has to be a point, say, around here. Let's say I call it R. And at R, the gradient here of the tangent would be horizontal. In other words, it would be 0. So we would just need to set dy by dx equaling 0, okay? So if we did that, then with a fraction like this, the numerator must equal 0. So therefore, from that, we would have y minus x equaling 0. Rearrange this, make x the subject, you'd have x equals y. And what I would want to do then is take the equation of the curve, which I'll call 1, and y minus x equaling 0, when it's rearranged x equals y, we'll call it 2. Substitute for x into here, solve simultaneously. We're going to get an equation in y, it'll be a quadratic equation. We'll get a positive and a negative value because the negative y value would correspond to a point down here on the curve, okay? Its y coordinate would be negative. So we would solve them simultaneously, take the positive y value, substitute it back into this equation and take the positive x value. And that would give us the coordinates then of R. So in summary then, what we'll do is solve 1 and 2 simultaneously, taking the positive x and y values. Okay? Okay, so for this question, we're given this differential equation and these initial conditions, that is that h equals 5 meters when t equals 0 seconds. And we're asked to show that h equals this result here. So how do we do this? Well, we've got a differential equation where we can separate the variables. So I'm assuming that you're familiar with this technique. If not, do check out my video tutorials on separating the variables under differential equations on my website, okay? Or on my YouTube channel. Right, so assuming you're familiar with that then, we've therefore got, well, I'm going to get rid of the 40, multiply both sides by 40. We want to bring the h's to the left-hand side, so I need to divide both sides by h. I could write 40 over h here. I'm not. I'm just going to leave it as 1 over h. You'll see why in a moment, but it's up to you. You don't have to do this. You can just leave it, as I say, as 40 over h. We've got the dh there, okay? I need to get rid of the dt, so I'll put it on the other side, and I'm left with the cosine then of 0.25t, and the dt goes there. And I integrate both sides. So by pulling out the 40, it just means I'm left with the integral of 1 over h, okay, as opposed to 40 over h. The 40 is a constant, so I can do that, okay? Integrate the other side as well. So all we need to do is just integrate this, get our constant of integration, substitute our values in to work out what the constant is. Hopefully then rearrange our equation and head towards this result. Okay, so that's the method. Now we're just going to integrate the 1 over h. Should be familiar with that. That's going to be the natural log of h. So we've got 40 times the natural log of h. Normally I'd write these in a mod sign, but h, remember, is a height. It's going to be positive in this example. And so I don't really need to put mod signs there. Integral of cosine is going to be a sine function. That function is going to be 0.25t. But remember, we need to divide by the 0.25, that constant in front of the t. So 1 divided by 0.25, well, that's the same as 4. Okay? And then we've got the constant of integration. And you can put it either on the left-hand side, plus c, or you can put it on the right-hand side. It's up to you. It's plus c. I did a tutorial on that, on does it matter which side you put it on? The answer is no. If this constant here turns out to be 5, and I had put the constant on this side and worked it out, it would have turned out to be minus 5. Okay? So check it out for yourself. It doesn't matter which side you put it on. All right? Now, I'm going to work out what that constant c is by putting these boundary conditions in. So let's just say we call that 1, and we've got our equation here 2. So just going to say sub 1 in 2, okay? And that will allow us to find our constant c. So if we do that, we therefore got 4t then, natural log of h, which is now 5, okay, and we get 4 times the sine of 0 plus that constant of integration plus c. Well, the sine of 0 is 0, so that means that we're therefore left with c equaling 40 times the natural log of 5. And I want to substitute this back into equation 2. And what does that give us? Well, we therefore have 40 times the natural log of h equals 4 sine of 0.25t plus that constant, which turns out to be plus 40 times the natural log of 5. And as I said before, if you put the constant c on this side, done the same thing, you would have found that that c would have turned out as negative 40 times natural log of 5. Okay, so it makes no difference in the end. Right, I can see that we could divide throughout here by 4 actually to each term. So I'm going to cancel that out. That's going to be a 10. That's going to be 1. And that's going to also be a 10. And when you're working with log equations, you need to bring the terms containing the log to one side. So if we just come down here, right, what we're therefore going to have is if we subtract 10 times the natural log of 5 from both sides, pull out also a common factor of 10, you can see we're going to have 10 times the natural log of h here. Then we've got minus 10 times the natural log of 5, so I just need to write natural log of 5 there. And that's going to be left with equaling sine of 0.25t. Right, okay, where do we go next? Well, we can use the subtraction rule for logs. That turns out to be 10 times the natural log of h divided by 5. And that's going to be equal to that sine of 0.25t. And now I could divide both sides by 10, and I can see we're getting closer now. We've got the natural log of h over 5 then equals 1 divided by 10, which is 0.1. So this is looking good. Sine of 0.25t. Now at this stage we need to take the inverse log of both sides, anti-log both sides if you like, and that leaves us with h over 5 equals e to the power 0.1 sine of 0.25. Should be familiar with that rule in logs, okay? You can see we're nearly there now, because if I multiply both sides by 5, I end up with the result that we've got to prove, that h equals 5 times e to the power 0.1 sine of 0.25t. Okay, so I'll just tidy this up, just border this off down through here, and there you go. Okay, so I hope you're able to do that one. If not, at least seen how to tackle it, okay? Now in this next part, we've got to state the maximum height h. So what can it be? Well, very easy, because there's no working really needed at all, because this function here, the sine function, is the thing that controls h, and sine can only go between -1 and 1, and so therefore we want this to be a maximum when we're multiplying the 0.1 with 1. Okay, so the maximum height has got to be 5e to the power 0.1. Okay, and don't forget the units, it's measured in meters. All right, you might want to work that out as a decimal. If you do, it's going to come out at 5.525 and so on. Or if you do that, you need to round it up. Let's say you round it up to 2 decimal places. That's going to be 5.53 meters. Don't forget those units again then, to 2 decimal places, 2 dp. All right, so there we go. That's how we tackle that one. Now for this last part of the question then, we've got our equation for the height h, and we're told that when t equals big T here, seconds, h is a maximum for the second time, and we've got to find that value of t. Now in the previous part of the question, we saw that the maximum height h was controlled by the function sine of 0.25t, because the sine function can only go between -1 and 1. And so we get that maximum when the sine of 0.25t is 1. Okay, so that's where we start. We have got the maximum height. Let's just put it down here. Maximum height, okay, is when we have the sine of 0.25t equaling 1. And so we've got to solve this equation, work out a series of values for t. We want the second solution in our series of values. So we just need to take the inverse sine then of both sides. So we're left with 0.25t equals the inverse sine of 1. And we should be familiar with this result, the inverse sine of 1. If we just draw up the graph, you can see that the inverse sine of 1 is going to be pi upon 2. 90 degrees if you're working in degrees, but we have got to be working in radians here, okay? So we need to take pi upon 2. So therefore we have 0.25t equals pi upon 2 radians. But that's going to be the first time when we get the maximum height h. We want the next solution. Well, that's going to be at this point here, and that's going to be another pi upon 2 further on from the 2 pi. So if you add 2 pi plus another pi upon 2, you're going to get that second peak there at 5 pi upon 2. So that's the time that we want, 5 pi upon 2 there. I say that's the time, that's not right, that's the solution that 0.25t would be. So we can see that when t equals big T, we can see that 0.25t, that's 0.25 times big T there, will equal 5 pi over 2. And if I multiply both sides by 4, you can see that I end up with t equals 5 pi upon 2 times by 4. That's going to give me the exact value of 10 pi. You might want to have this as a decimal. If you do this on your calculator, you'll find you get 31.415 and so on. And if we round that, say, to one decimal place, it's going to be 31.4 to 1 dp. I haven't put the units in here as seconds purely because we know that t was measured in seconds, okay? So we just need to quote the value of that. 31.4 then, when it reaches its maximum height for the second time.